Oh, you absolute legends. This is a discussion trying to relate three things together: intermolecular forces, temperature, and phases. Phases being solid, liquid, and gas. Intermolecular forces are the forces that occur between molecules. We are not talking about ionic and covalent. We're talking about dipole-dipole, hydrogen bonding, dispersion forces, the forces that can occur between molecules that are identical or like each other, or between molecules that are in solution with each other, the intermolecular forces right there. So let's kind of do this one piece at a time, because we do have three things to juggle, but let's not juggle all three at the same time right now. First thing to discuss is intermolecular forces with respect to the temperature. So let's talk about boiling point, because a boiling point is a temperature where an intermolecular force is broken. So we have, this is acetone right here, this molecule. Acetone has, the hydrogens aren't shown. There's 3 hydrogens on each of these carbons here. But this is acetone. Its intermolecular force that can occur right here, I'm sorry, it has a boiling point of about 50 degrees Celsius. And this is water right here, H2O. And it has a boiling point of 100 degrees Celsius right here. So from these temperatures of boiling points, we can infer something about the intermolecular forces. Because this is a higher boiling point and it takes more energy to break the intermolecular forces, water must have stronger intermolecular forces. I'm going to just abbreviate that IMF. And this has a lower boiling point, so it must have weaker IMFs, intermolecular forces. Now, in all of this time, we have made a deduction about the intermolecular force strength relative based on a temperature alone here. Okay? Now, this is useful because it's a quick and handy way to determine, without really knowing anything about the molecule, you can make some correlations about intermolecular forces here. Note that we haven't stated what is the intermolecular force that can occur between water molecules. And we haven't stated what is the intermolecular force that can occur between acetone molecules. We are just saying based on the boiling point here. So that is a correlation of intermolecular force and temperature or boiling point. Let's consider something that involves phases. Let's use water again. Now, water at room temperature, atmospheric pressure, all that stuff right there is a liquid. Now, I know that water can exist as a solid, liquid, and a gas at TP, standard temperature and pressure, but for the most part, you don't have to put any energy into water to find it in liquid phase in nature. You just find it right there. So, water in liquid phase. These pink dotted lines represent the intermolecular forces that are occurring in liquid phase. You know, a network, a web of forces that maintains liquid phase. Let's compare it to oxygen, O2. Now, for the most part, you find oxygen in gas phase. And again, these pink lines are meant to represent the intermolecular forces that can occur between the molecules, a webbing connecting molecules to one another right here. Now, from the phase of matter, we can make a statement about the strength of the intermolecular force. Liquid phase matter, the molecules are closer together, and it is stronger intermolecular forces, IMF, than gas phase. Again, we are not stating what the intermolecular force is. We're not stating whether it's hydrogen bond, dipole-dipole, or dispersion. We are just using a known fact about its state of matter at standard temperature and pressure, what you know. Anything that is in liquid phase, you can predict that it would have a stronger intermolecular force than anything that is a gas phase. And if we had a solid out here, a solid would be stronger still than liquid. You know, solid, liquid, gas is kind of a rate of hierarchy right there. So this was an example of comparing intermolecular forces and the phases of matter. Solids, liquid, solids, and gases. Note that there's no temperatures listed on here. Okay. Let's try to throw all three together into a more complicated example here. Let's go back to our acetone and water examples. Here is our water example, and here is our acetone example. And we're going to try to put all three of these together right here. The intermolecular forces, a statement on the temperature, and a statement on the phase here. So the intermolecular forces that are present, that can exist in between, when you have hundreds and millions and billions of acetone molecules, dipole-dipole interactions are going to be the strongest intermolecular force that can exist. Hydrogen bonding is what can occur between water molecules. When you have hundreds of millions and billions of water molecules, hydrogen bonding is what can occur right here. Now, the question is, which will have a lower boiling point? Which of these will have a lower boiling point? We know about the hierarchy of strength between hydrogen bonding, dipole-dipole, and dispersion forces. And you should be able to rank these by increasing to decreasing strength here. Hydrogen bonding is the stronger IMF. Then dipole-dipole. Dipole-dipole is the weaker of these two. Now, how can this help us predict a boiling point? The weaker intermolecular forces of dipole-dipole would take a lower temperature to transition from liquid to gas phase. A boiling point is nothing but a temperature where a substance goes through a phase change of liquid to gas. The higher or stronger intermolecular force will have a higher boiling point. This one's going to have the lower boiling point. And that is based on a analysis of what intermolecular force is stronger when comparing these two here. That's a lot. I hope that helps. Thank you.